Hello! Today we are going to introduce rotational motion. We've already seen a little bit of rotational motion when we had the unit on uniform circular motion. But that was something that was already moving in a uniform way. Now we're going to talk about rotational motion that is changing. So say speeding up or slowing down. Just as we had a definition for linear speed. Recall linear speed, we used V, was change in linear displacement divided by change in time. This is angular speed, and so this is not a W, this is a Greek letter omega, is the angular displacement divided by time. And just a refresher, I know we've covered this before, but angular displacement is the angle that an object rotates through as it goes through an arc. So that this delta S is my arc length and R is my radius. So this is called the angular displacement. If these are both in, say, meters or both in centimeters, angular displacement would be in radians. Now, I will say if you are not really familiar or comfortable with going between radians and degrees and revolutions, and if you need a refresher on your unit circle, I have a separate video that goes over the unit circle. So when we defined linear speed or linear velocity, right after that, we defined linear acceleration. And you'll recall linear acceleration, which we used a lowercase a, was the change in speed divided by the change in time. Or if we're talking vectors, change in velocity divided by change in time. So this is my unit for angular acceleration. It's a Greek lowercase letter alpha, and it is the change in angular speed divided by the change in time. So very similar, and good news, all those problem solving skills that you developed when we did linear values are going to apply to these problems as well. Now I know that we covered these equations before as well, but just as a refresher, if I want to go in between or connect linear speed to angular speed, the linear translational speed, that's what that lowercase t, is going to be the angular speed multiplied by the radius, where the radius is the distance from the object to the axis of rotation. And the linear translational acceleration is the angular acceleration multiplied by the distance from the object to the axis of rotation. That's what my R is. So if I had a circle, maybe let's think of carousel, with a horse here and a horse here, and they're both rotating about an axis in the middle of the carousel. The R's for those two adjacent horses, side-by-side horses, would be different because they would have a different distance to the axis of rotation. And so that's what R is in that equation. After we defined these in linear quantities, what did we do next? Kinematic equations, right? So we have rotational kinematic equations. Do these look familiar? Yeah. I've written up here so we can compare. These are our linear kinematic equations in one dimension. You have mastered problems with the linear kinematic equations in 1D and 2D. Recall when we did 2D, we had a set of these for X and a set of these for Y. These problems are actually a bit easier because we're only going to have one set. So this is the angular speed equals the initial angular speed plus the angular acceleration times time. So we're going to use these equations to relate angular displacement, initial angular speed, final angular speed, time, and angular acceleration. So you'll be given some of those and asked to find others. Let's work some problems now.